Thank you for joining today's technical breakfast briefing. My name is Pradap Rajagopal. I lead a global solutions architecture team at Ciena, and I'm focused on our routing and switching solutions. I want to welcome you to the next installment of our technical briefing series. These are intended to provide education on a variety of relevant topics, primarily focused on the IP community within Australia and New Zealand. After 3 sessions on SRv6, which were recorded and are now posted on YouTube, we are now shifting gears for the next installment. And in today's session, Aman Balla will talk about optical basics for IP experts. This will also be a multi-part series on this topic. To let you know, we are recording today's session and these will be posted online. In terms of questions, please do ask questions throughout the session using the text-based Q&A. We'll either take these during the call, and if we don't have time, we will follow up individually as we have done in the past. A quick introduction on Aman before handing over to him. Aman is a senior architect based in Melbourne. He's responsible for creating sustainable and scalable transport solutions for Ciena and works very closely with our customer base here. We do have a lot of material to cover, so without any further delay, I will pass over to Aman to take us through the basics of optical technology. Over to you, Aman.
Thanks, Pradap. I appreciate it. Morning, everyone. Evening, afternoon, if it's other part of the world. So as Pradap mentioned, today what we are going to have a interesting discussion on, on an optical basics for IP expert. Before I start, thanks for your time for this morning. So as there's quite a fair bit of material to go through, so let's get right into it. So first and foremost thing, when I was having a chat with some of my customers about this upcoming discussion, the feedback I got from them is like, essentially some of the people on the other side of the technology, usually, it comes like, okay, what does light and mirrors do to my data? And if I can understand what happens to my information which traverses through this cloud, can I use that information better to optimize my end-to-end network? So in today's session, I'll say in today's part 1, we are trying to demystify what happens in this cloud. And as we progress further towards the end, I will show that what we'll talk in a part 2 of the series. So let's get right into it. So the first thing which is on our agenda side, so we'll just go through understanding first and foremost why we are having this discussion even today is there's a lot of focus going on IP and optical convergence. So let's just try to understand the meaning of it and why that is relevant. Then after that we go towards why should IP people care about optical network, in which basically I will talk about the various impacts of optical network can be on your choices on a technology and what you select on your router platform and how you select those optical network considerations can help you. Then we will go into the functional component of optical network that will, what are the various components and what are their roles in place. And towards the end, we will see more on evolution of a technology. It has come a long way. It has come a long way, and how this technology has evolved all this while. And then after that, we will just quickly see, what we'll talk on a part 2 of this webinar. So first and foremost, what does IP and optical convergence mean? Whenever I have this chat with various people, either it's on our product line management within Ciena or on our customer base across globally, there's a different understanding. Different people are trying to achieve different things with the IP optical convergence. The first one they are trying to do is automation for service management and more. More could be operations, more could be assurances. Then some people are trying to, have simple operations, basically a single pane of glass when I'm doing a service provisioning, or even when I'm trying to manage my network. Can I have one application which can guide me through both sides of the network? Which is, when I say both sides, I mean like layer 2, layer 3 to all the way across layer 0. Third one is pretty interesting, multi-layer control plane. Control plane exists as every single layer, well, at least up to layer 3 of the OSI model. It exists over there. And then the point comes is like, so far, historically, these control planes haven't been talking to each other. What can be achieved when they talk to each other? So that's another part of the convergence. And the third one was platform convergence. Through IP optical convergence, can I get rid of some components on my network chain or what I'm deploying in a network? And once I get rid of them, what could be the benefits? So that's a third part. Various agencies have conducted various polls, but what I have gathered so far from my interactions is, and one day I would like to hear more broader view as well, is that, the first point is the point priority number one, where people are trying to achieve more automation for service management and more. Then simple operations and multi-layer control plane is becoming a priority too. And then platform convergence, which is more on the hardware side of the platform convergence, is a priority 3, leading towards a sustainable networks, or I should say overall reducing a TCO of what they deploy in the network as they evolve on the journey. That's a priority 3. So this is what we have discovered so far. Now, key point, why should IP people care about optical network? So on a top left, we are seeing a very simplistic view of, what is the chain of a network, like how optical network is how two routers are connecting via optical transmission network. We will be dissecting every single element over there in next few slides. But just for now, if we talk about, this is the point number 3 was our hardware convergence. If we get rid of transponders and move towards a small little hand-sized plugs, which I can plug directly into my router and have an ability to send out a direct colored wavelengths to the optical transmission network. That's a key thing. And what are the considerations we need to make? So whatever happens from transponder to transponder is going to impact decisions you make on your router technology selection. So for now, what we are seeing is that, routers use gray plugs, which can be 10 gig, 100 gig, 400 gig, 800 gig, these gray plugs, well, not 800 gig yet, but we are reaching there. Many places, even it has started to show up. When they connect into transponders, then what are the impacts to the data? And most importantly, when you start replacing them with the colored plugs, with the wavelengths, what considerations you need to make? So the first and foremost thing is about the form factor. There are various form factors available, and each form factor has its own pros and cons. And these form factors are going to dictate your operating expenditure. And then, also as you move from gray plugs to colored plugs, there is going to be increase in your thermal limits and your cooling limits, which are, your rack limits, which you have. And those are going to be important as well to keep consideration. Second one is on the line rate. Now, and the line rate which you can actually select depends or will going to, impact your router port efficiencies. So for sake of discussion, if your router port can provide you 4 ports of 400 gig, and when you start to go from location A to location C, but because of the optical impairment or optical transmission network, you're not able to actually achieve 400 gig, then you are compromising on your router port efficiencies. And that impacts your capital expenditure, the money which you are spending on selecting a router platform. So that's a point number 2, which you have to keep in mind. And a third one is more holistic. Now, again, if we are not really able to achieve the best rate coming out of the DCOs to begin with, to go from A to Z, then eventually what's going to happen is we reach towards a place, either you have to deploy more fiber or you have to lease more fiber. And when you do either of these 2 things, then you deploy more optical line system into a network. And when I say optical line system, we are starting from this particular point to this point, which means that you are putting more electronics in your system, and these more electronics will be totally different, will be taking you away from the goals of your sustainable network. So these are the 3 key hardware, I will say, or I should say that, quite business-oriented considerations one has to keep in mind. Going on further, there are more, like, if we move away from the business side, but we now start talking towards operation side and the network running side of the world, what could be the points you need to consider? So the first and foremost thing is visualization. If we move towards IP optical convergence, understanding of your optical underlay for IP services, and can you have one single pane of glass to demonstrate that, show you that, once your signal leaves from router and goes all the way across other side to the other router, how that enables, how you can visualize it. And it can also enable a, holistic planning of a layer 0 to layer 3 infrastructure. Second point comes as a service assurance. So layer 1 and layer 0 network, they have their own network alarms. They have their own performance monitoring points. Now, how these performance monitoring points can impact your services, and to what level can you ignore them, or you can correlate with the IP layer alarms and services to understand, to provide more service assurance. Third one is most important, I'll say, multi-layer control plane. If there are different decision mechanisms happening and every single control plane is running its own path computation engine, the end result might not be as optimized as one would try to achieve so or hope so. So understanding multi-layer control plane is really beneficial as well. And in next few slides, I will talk about what is a photonic control plane and how having a knowledge between the two multi-layer control planes can help in optimized planning. So that was more about, on the operation side of the world, for why IP people should care about optical networks. Okay. Now let's start dissecting a links, So very simple view of optical network link over here we have in between, and let's see what is the role of every single component over here. So to begin with, the most underrated element, I will say, it's even, quite many times it's passive as well, depending on what has been deployed in a network. So this is where everything starts, filter or array waveguides, or it can be colorless mux, demux. There could be a complete new dedicated section to just talk about this, but I've just tried to keep it a bit more high level, is that, its role is get multiple inputs, multiple wavelengths from various transponders or colored plugs of individual wavelengths, and just multiplex them into on the fiber and send it across on the other side. Historically, and even now, many of these are passive. So you don't even get to know, if you look at from, you just look at your IP service, you'll not even get to know that it even exists there till the time your friends from the optical side of the world tell you about it. Second one is the amplifier nodes. Extremely important when we talk about either a challenging fiber in a metro domain, or we talk about, really long links or ultra long haul links. The whole point is optical signal is coming in, you amplify that, as the name suggests itself, amplifier nodes, and send it out on the other side. Having said that, as amplification happens, it also increases the power of a noise. So it's really important consideration, how many amplifiers, or at what distance you need an amplifier, or what should be the gain of amplifier as you start going towards the planning of your network. So that's another important point to keep in mind. And now we move towards to complete the link. So essentially from the router side, we are seeing various signal coming in. Could be 800 gig, 400 gig, or 100 gig. That usually goes into something we call on optical side muxponders, and that sends out a signal on the other side. So we'll start talking about transponders now. Two types. Either we call it transponders or we call it muxponders. The role of transponder is whatever client comes inside, I'm just going to put a wavelength on top of that and I will send it out. Whether it's 100 gig, 400 gig, or 800 gig, and historically there were actually STEM 1 or 10 gigs as well. And then it comes towards the second role is now, second variant is muxponders. A point of a muxponder is take various type of signals all the way from a 10 gig to 800 gig. Now, various vendors have various technologies, but I'm just generalizing over here. anything from a 10 gig to 800 gig, and then put it on the line side, which can be tunable up to 1.6 terabytes. That's what we have started to hear our industry, but could be various options again on the line side. But that's generally the high-level view of two variants, transponders and muxponders. As you know, the routers start feeding into, that's the first point of contact for the routing signals which come inside on optical transmission networks. Just a bit of appreciation. How do you select these expanders? What are the performance metrics? So some of the things which need to be considered is like, okay, what is my maximum rate it can give me? What's a tunable granularity? When I talk about a tunable granularity, as you see that, it can tune up to 1.6 terabytes, but you don't want to deploy that if you don't need it. For example, if you need only 400 gig, you don't really want to start spending money to have a 1.6 terabyte. So can I have what's a granularity of the tunability in between? From 400 gig, can I go to 450, 500 gig, 550, 600? And what are the step increases I can have? Second point is reach of this expander. As technology evolves, that what is a reach I can go up to without regenerating. Regeneration is the biggest enemy. That involves, as you regenerate, you will be regenerating as every single wavelength level, and that means more electronics, and that just takes your TCO off the charts. And then comes as a line rate encoding. Am I getting an Ethernet encoding, which has its own benefits, or am I getting an OTN encoding, which is better for manageability? So that depends on a line rate encoding as well, which choices it can give me. Does it limit towards one point only one particular encoding, or it takes me on both? Further, just a thumb rule on how we determine reach of expanders. So simple thumb rule is, it's really complex topic, but a simple thumb rule is, if I have a signal coming from one side and I have back-to-back two similar expanders, their line sides, right, sitting at the same place, back-to-back connected to each other, and I have a test signal on the other side, then there is this magical value known as optical signal to noise ratio. What is our optical signal to noise ratio threshold of a transponder till the time it stops recognizing the quality of a signal, and all it gives me is a complete noise only, or it can detect from that? The guideline is lower the better. So let's say if someone comes and says that my OSNR, back-to-back OSNR is 29 dBs, and someone else says mine is 27 dBs, 27 dBs is better than 29 dBs. It will be able to provide you extra kilometers to go from one place to another, which means that it will be able to provide you ability to have some patches of bad fiber, or to not have regeneration. So that's a reason. This is usually the performance guidelines one needs to keep in mind. Going on forward, one of the things which I did not cover in a previous slide on a component was a ROADMs. It definitely needs its own dedicated place. Most important, at a high level, it plays two roles. Whenever you start having a mesh in your network, or you need to start traverse from, let's call it point to multi-point logically, but physically it's the ROADMs which are able to do that, which are able to steer a wavelengths which you are receiving to the other side at the optical level, known as optical switch node, or a ROADM, or a wavelength selective switch. And essentially it is able to do at a wave. Why do you need to do at a wavelength level? Is if you do it, you are avoiding expensive electrical regeneration. Always remember, whenever we are regenerating or we are terminating signal without connecting to a client, and just so that it can pass information from a one incoming degree to another, or I should say one incoming direction to another, that really increases your capex and opex as well, because not only you will be buying more electronics, you will be also paying for a more electricity to running those electronics. So that's a first role of ROADMs. Second role of the ROADMs is like, as your channels go across a long chain, various wavelengths will have various attenuation. When I say attenuation, some wavelengths will be impacted more and will reduce their power as they traverse along compared to other wavelengths. So job of a ROADM after is to, equalize them after some time. Because if this difference between the power level increases, by the time you reach towards the end, it becomes really difficult for system to understand good part of our incoming signal from noise. So that's why you need gain equalizing. Really high level thumb rule, 3 to 4 amplifier nodes, you need ROADM in between to gain equalize. But again, an important consideration is too many ROADMs on a link can cause penalty as well. It's almost like a friction, optical signals, the way their power loses, it's almost like a friction. Every single time it goes from a one component to another, at a layer 0 level, they will be losing some power out of it. So that's a reason that, too many ROADMs have come into a play. It can cause more penalty in your links, which can be countered by high-performing transponders or coherent plugs. So different considerations. And at the end of the day, it's completely balancing act. After having a look more at any level or a hardware level, let's see control plane, photonic control plane specifically. Now, photonic control plane is something like, which I'm sure this is something we all are aware of, especially at the layer 3 side. You've been using it a lot, right? Its whole point is that, nodes talk to each other, tell them about this, I am Y, I am X. This is what is my topology. These are my near endpoints. You should know it when you start running your path computation engine. And the role it plays is automatic service provisioning. So like, service management, automatic service management, you don't really need to select that I need to go to C, G, F to go to H from A. But if you just tell them that, give me the shortest path or give me the path with the least resistance, or, actually this end customer is not really paying me as many dollars as I would like to have. So what I want to do is I want to go through this path, or this traffic is not that important, or it's not that critical, let it go through the longer path. So that's one of the reasons control plane can help various constraints to steer along its own path computation engine. But when there's a fiber break, we all know that, unfortunately, it happens. It will steer it automatically. It will provide automatic restoration without you have to manage and find the frequencies along the path. It will do that job for you. So that's essentially what photonic control plane does. How is it different from higher layer control planes? When I talk about a higher layer control planes, I'm talking anything from layer 1, 2, 3. Anything above layer 0. So essentially what's happening is that, I have my client port, then there's this switching fabric. Switch fabric can be layer 1 switch fabric, 2 or a 3, but this is at electrical domain. And then the switch fabric aggregates or connects to the various line sites. To keep things a bit more simple right now for our discussion, let's say these line sites are either transponder or a colored line ports, doesn't matter. Or it could be even a gray line ports, doesn't matter. The whole point is switch matrix is a decision maker at this level. Now, usually on a mesh network, as many line sites or the degrees which are going out, those many colored line sites or the line out ports you require in order to support multiple fiber cuts. So that's thumb rule. Now, what happens in a layer 0 control plane is there's a client port, then there's a protection switch, which basically splits into only 2. Important point, only 2 line sites, one main, one working. And then there is a ROADM, which is playing as, again, in this specific instance, role of an optical switch. You always need a switch whenever it's a control plane decision, whether it's at a layer 1, 2, or 3 level, or whether it's at a photonic level. And now this ROADM decides how I send my wavelengths from incoming wavelength from one to another. What happens now as bandwidth increases, which is we all are very well aware of is happening because of I usually think whatever happens on the edge will impact your transport. So there you go. Now, as your bandwidth increases, you have to start investing as many number of line ports on a high layer control plane side to have similar level of resiliency as compared to on a photonic control plane. So that's a first CapEx consideration one needs to make. Having said that, you get on a higher layer control plane, you get more flexibility or a granularity. But it's a very careful decisions one has to make that, if I'm getting all I'm getting is like a 400 gig clients or 100 gig wavelengths, and those are the wavelengths I'm steering all across, do I need aggregation? Or if my client traffic is really a lot where I have 10 gigs or the more subrates and I do need aggregation, so those are the important choices one needs to make really. What is good, what is bad, I cannot say that. It depends on a case to case. But as we move towards convergence, this multi-layer awareness is really important now. Now, if you imagine a situation when layer 3 level PCs at that control plane are aware of what's happening at my layer 0 level, and then they can use that information to make their routing decisions and their path computation engine decisions, PC decisions for the paths they want to take. That is going to be really important, right? Because then you can, if you can make a route decision based on fiber quality, even make it better, real-time fiber quality, or a latency of a path. Maybe you had a one particular fiber length on a day one, but then these went through multiple cuts, and this suddenly 80 kilometer has become 100 kilometers because of the, adding more splices, adding more spools in there, and then you make those decisions. That would be better, right? So that's a reason multi-layer awareness between the two is becoming quite important now, and a lot many of our customers we are seeing that have already started working on this. Going on further, evolution of optical technology. Now, if we start looking at evolution of optical technology, and we have to really go back, from let's say 10 years back, it has come a long way. The biggest thing which we are hearing, a buzzword we are hearing is, which covers the whole link. So you will see that I'm using again same span chain which I used earlier. So the biggest evolution which has happened is from complete end-to-end chain is on a, so far it was C-band spectrum was available. That was on a whole wide optical spectrum range, only C-band was being used, 4.8 terahertz, I would say, as a utilized on a fiber band. And whenever the C-band was exhausted, customers will go back, put a new fiber link on these new fiber link, use another pair of fiber and put more electronics, more optical line system, and go further. Latest advancements have made us L-band available as well, which has almost doubled the capacity to carry, to utilize your optical fiber assets. So when I'm saying almost double, you can say that 4.875 to it's 4.825. So it's kind of almost double. It's not completely 2 times. It's almost reaching there. So the key thing to understand is that as this evolves, now the new decision which our customers are making is like, this also becomes a bit more nuanced. They're making is, do I completely buy a platform which has to be rip and replaced, or which can be upgraded with the add-ons? When I do this, what would be the impact on the traffic which I'm already running on my C-band? Those are some of the things which needs to be considered. So that's the first evolution on optical side, which covers a whole wide range of products whole wide range of components of the chain. Now let's start going one to one, how each individual components we have discussed have been evolving so far. So first one, again, I'll start with the filters. So it started off with the, it used to have 52 gigahertz only variable value available. But now as your wavelengths which come out of your transponders, they have started to have various channel widths. So you need to even have a filters which can accommodate various channel widths. Otherwise, what one will end up doing is they will waste a valuable spectrum on optical fiber. Second thing which has started to happen is, remember a few minutes ago, I said friction, optical signal, whichever components it goes through, it encounters friction. It will lose its power. But the way components been evolving, how much power is lost is starting to get reduced. So a lot of component manufacturers have have evolved their new products where we call it insertion loss. There's a reduction in insertion loss, and then as always, form factor reductions have been happening on this as well. Amplifiers, again, my favorite one, because what we are seeing over here is whole point of the amplifier was that I get a X amount of a signal coming inside, and then I'm going to amplify that, and I'll send X plus out. But again, with the component technology evolution, this gain of a X plus has started to become X plus plus now. So that's a one evolution point which we have seen. Another thing is, convergence is not just IP and optical. Convergence happens all across, right? Means it's various components. If they start doing the rule of the other components, and that can enable our customers to reduce their cost, why not? Let's use that, right? So another thing is assurance components have started to add it into the amplifiers. And when I talk about assurance components, I'm talking about fiber monitoring capabilities. How about if I can have my integrated OTDRs in my amplifiers itself, which can detect fiber breaks, and these fiber breaks can be communicated to the control plane so that they can start the reroutings. Or these fiber breaks can enable us to pinpoint that where the break has happened, so my operations team can quickly go and patch that out. So that's another. Mostly, as your signal travels, though I'm showing as it's a one fiber pair end to end, right? But it's always like one fiber goes in a transmission, one is on a receive, and you need amplifiers on each direction. So another thing which has happened is an integrated module for the both line side into one module, which just simply reduces your TCO. So that's another evolution we have seen happening. Now, another thing which we saw was remember a few slides ago, we saw that the component ROADM plays a part of equalizing a gain of wavelengths, basically bring all of them to the same level so that they can again traverse across few kilometers or many kilometers and tolerate the discrepancies. But ROADM is definitely expensive. So if I talk about a cost factors, filters are usually cheaper than amplifiers. ROADM and amplifiers are usually cheaper than ROADMs. But the best way to use ROADM is for optical switching or steering a wavelength. But if you just deploy ROADM for a gain equalizing, which has been happening for all this while, then you're losing out on quite a valuable money for just gain equalizing. So another integration effort has happened is, how about if I put that capability into my amplifiers? If I can have my amplifiers do that job also, that would be helpful, right? You don't really need ROADMs over there on a chain of optical link. You can have that amplifier. Now, this specific one, I should have used a different color, but this specific one can be component-wise different than the other ones. But it is still going to be much more TCO beneficial compared to the rest, compared to ROADM, sorry. So that's one optical evolution. That's another part. Now I will go on ROADM, which is again has gone through multiple evolution strategies, multiple evolution phases, right? So the first and foremost is degree. What we call a degree. Degree is usually a one particular direction coming out of network element. Now, if we talk about a one ROADM degree, it's not just one module. It usually comprises of multiple modules. There's a wavelength selective switch, which is actually a component responsible for steering a wavelengths. Another one is an amplifier, so which basically adds more juice to the incoming light and sends it out. Then there's a OSC, which is a supervisory channel, optical supervisory channel. And the rule is that, for our monitoring capabilities, And the third one was, OTDR, which was a fiber monitoring capabilities. So these all components together make a ROADM degree, and they all carry their own cost value. They all carry their own, point of failures, and they all also have their own power consumptions. So the biggest one evolution which has happened on the ROADM side of the world is like component integration, which has evolved to give the better TCOs. Second one which has happened is that number of degrees on a ROADM. Now it's just like how you have your traffic junctions. Sometimes you have a traffic junction which only has a one incoming and a one outgoing, then the third added path gets added, a fourth path gets added. And especially as we go on a metro environment, or even on a long haul, we see that you need many more incoming signals, you need more incoming directions, incoming and outgoing. So having more degrees on a ROADM is definitely another which increases scalability for your traffic. So these two integrations are enabling more higher mesh connectivity and more sustainability, these two innovations. And the third one, which I've captured over here, is interesting because that's not from, excuse me. The third one is more important because that has nothing to do with technology. It's more like the way you are utilizing technology. So we started with a very kind of a fixed architecture where my one transponder signal, which will go from a one side, cannot go to another. Only thing you can have is that if my one wavelength comes, it will steer to the other ROADM. So it was kind of a flexible, still it had its own fixed architecture. Then some smart cookie came and said that, how about if I put the similar ROADM at an add drop layer itself, then I can have a capability of sending my wavelengths all across on a multiple degrees. So that was our first evolution, the way you started utilizing these optical switches, and that this evolution actually enabled photonic control plane. Now what we are witnessing is optical fabric evolution spread all across a metro environment. Now imagine if you have 7 to 8 nodes into your optical network in a metro, one particular metro city, and all these nodes are talking to each other. But there is a capability to steer your wavelength, your enterprise traffic. Let's say this traffic wanted to connect at a, for sake of discussion, 100 gig level or a 400 gig level at any particular wavelength level to a one cloud provider. And then they want, okay, this is not working out. I might be getting a better deal with the other cloud provider. Now I'll go to them. With this, the way they have started utilizing with the optical fabric using the ROADMs, that can be made available. So this is an application evolution we are seeing, and not just a technology evolution. The way you use technology is another application evolution we have started to see, having an optical fabric on one network domain. So that was essentially the part of end one of our discussion, and how these optical technologies are impacting our routing decisions. Now, what we have seen is really centric to what a layer 0 right now. In a part 2, what we are going to view is we'll start looking at more on a history. We'll start looking more on a layer 1 level, history of coherent technology and its evolution. We will go down on our history lines by at least 15 years. What used to happen before we started hearing these words coherent? What was non-coherent, and how coherent came along? Then, as we go from a transponder to coherent plugs, what should we deploy and where should we deploy? And when we deploy this one particular technology, especially for my friends on the IP side of the world, what should be the high-level performance things you should keep in your mind? And why can't you put a pluggable on a router like a gray plug? It's not that easy that, okay, I'll take my gray plug out and I'll put my colored plug in and it all works. There are more nuances you need to consider, more details you need to consider. And in the end, I will cover what is a vision of a multi-layer network management, and how we see that our customers are heading on that side. With that, the part 1 is concluded. Pradap, over to you.
Thank you so much, Aman. I'm impressed that you completed all that within the 45 minutes. So well done. There's a few questions that have come through. We've got a little bit of time. Maybe I'll start with the easy one first, because I think the answer's on this slide. Going back to the photonic control plane, how do we coordinate between a layer 0 and a layer 3 control plane? I think the answer was on that last slide, but I'll kind of let you answer that, Aman.
Okay, thanks for that. Very good question. So how do we coordinate? So it can happen at a various, there are now open standards coming along, not just like, communication between north to the south, which I mean to say that, packet controllers and optical controllers to orchestrator. There's a east-west communication happening as well. So optical controllers, when they can start, sending out information to packet controllers or layer 3 controllers, this is how my topology looks. You're connecting to this node, and these are its neighbor, and these are the optical parameters. When you make PCE decisions, this is what you need to know. So essentially, when this communication can get driven with the standard-based approaches, it's easier for both the controllers to talk to each other, or have a technology which can actually, pick up and make decisions for between the two sides. A bit more of an umbrella system.
All right, excellent. And I assume that's what you'll cover in that part 4 you said on the second part. The next one is a photonic control plane based on segment routing or RSVP or some other protocol?
So it's OSPF. The underlying protocols are OSPF, Open Shorter First. Historically, it's been present with the using Dijkstra's algorithm, which is essentially like, whichever is my shortest path, give me that signal first and open that one. And then the, little bit constraints started to come on that. When you start putting constraints, how do you define a shortest path? Is it a literal definition of a kilometers of link, or it is a definition based on a fiber loss, or it's a definition based on, what is cost you start assigning to it. So essentially, it's OSPF, which is the underlying technology.
Hey, excellent. One more question. In brownfield implementations, typically an operator has more than one principal. I assume that means vendor. How can a controller manage multiple vendors? Maybe that's an answer for the next.
Exactly. I was saying that because then I'll be pretty much covering that point number 4. So I'll keep it. I've taken a note. I'll answer that specifically on a point number 4 next time.
Excellent. And there's a couple more questions. One which is very specific to Siena's implementation. So we'll take that one offline because it's not really the intent of these sessions, but we'll absolutely follow up on that individually. Sure. And then another one on Siena's implementation. So we'll follow up on that separately. Sure. Those are all the questions I've seen here. If there are any other questions, please do send them through. You can contact either one of us through LinkedIn or any other mechanism. But with that, we're done with part 1. Thank you for joining today, and we look forward to taking you through part 2. So look out for that invite in the coming weeks. Thank you very much for your time, and thank you again, Aman.
Thanks for that. Thanks, everyone. Appreciate your time.